chloroplasts do make ATP, but as we will learn, the ATP that's made in the chloroplast just stays with the chloroplast. It doesn't go out and provide energy or energy to use for the plant. The plant has to take a product that is made by the chloroplast and then convert that into glucose so that the plant can then use it. But as we'll learn, the plant also can make all kinds of things with this substance that the chloroplast makes. So, you should understand the electromagnetic spectrum. Essentially, it's light. Electromagnetic radiation is light. It comes in all kinds of forms, from gamma rays through radio waves. And one of those groups is called visible light. It's a very small portion of the light spectrum. And this is what is most important when it comes to life. There's this stuff called pigments, and pigments absorb visible light. Now, these objects can reflect light, they can transmit light, or they can absorb light. And a pigment is responsible for absorbing visible light. When it absorbs some light, say in the red and violet spectrum, all right, what's left over are yellows, greens, and blues. Yes? Not yet. Yellows, greens, and blues. And these colors come together. So yellow and blue make green. With some more green, you get a greener green. All right? So, there you go. All right. Now, yes? Okay. So anyways, so if it absorbs all of the light, then what do we see? Black, yes. Black is the absence of light. So anything that you see that is black, what's happening there is no light is going back to you from that object. What?
Wait, so the people with darker skin color absorb the light?
Yes. Well, your melanin does. So that the photons, the melanin interacts with the photon in such a way so that the rest of the cell does not interact with it. So that's a good thing. Yeah. The lighter your skin, the more the photons can damage other parts of the cell. Yeah. So, next, we've got, and if I reflect all of the light?
White.
We see white. All light is white.
That's light.
Yeah. Alright. So, now we care about pigments because of this one pigment. The pigment is called chlorophyll A. Chlorophyll A is a pigment. It's a molecule. And chlorophyll A absorbs red and blue-violet light. Now, you see, there's a picture of a carrot here because there's also other pigments in plants, right? One of the other ones is called a carotenoid, and a carotenoid absorbs all the colors except orange, so we see orange from that. Right? But chlorophyll A absorbs red and blue-violet, so what we end up with are some oranges, some yellows, some green, and some blues, and that gives us the green that we see, the dark green. Alright. So, now these accessory pigments that exist, you're not going to have to learn about any of them because I'm not going to test you on them. Just know that they help out. They essentially, most of them, their job is to redirect or emphasize the photon energy towards the chlorophyll A. And the main thing that we're interested in chlorophyll A, that's what vibrates so violently that the magnesium itself loses an electron, right? And so that electron is able to do work. Right? So we're going to talk a little bit about that today. Now, it's important to understand that chloroplasts are found in plants and as photosynthetic proteins. So chloroplasts are only found in plants and photosynthetic protists. However, there are many photosynthetic bacteria, but the photosynthetic bacteria do not have chloroplasts. Right? The bacteria does, however, have structures and lots of enzymes that are also found in chloroplasts that do all of the photosynthetic processes. So a bacteria that does photosynthesis, so photosynthetic bacteria don't have chloroplasts, but they have all of the necessary equipment to do photosynthesis just hanging out in their cytoplasm, right? It's just floating around in there, free floating. So a chloroplast has a few structures that are important to know about. First one is a thylakoid. So a thylakoid is this one single little flat sac here. Right? And then thylakoids are found in stacks that we call grana. So a stack of thylakoids is a grana. And then they are all sitting inside of the internal fluid of the chloroplast that we call stroma. Now the stroma is really just the cytoplasm of the chloroplast. But because it is so unique in that it has many proteins and enzymes and such inside of it that are found nowhere else, we give the stroma a special name, right? They're not found outside in the cytoplasm of the plant. Okay? So we give the interior of the chloroplast, the fluid that's found inside, a special name called the stroma. Okay. So we have thylakoids that stack up and that are bathed in the stroma. So these thylakoids stack up in the grana, they're bathed in the stroma. Now if you look up here in this one, you can see this is a grana, right? These little dark parts. Right? So what they are, they're just stacks of thylakoids. Alright, so now you may have in the past learned about photosynthesis and learned the chemical reaction for photosynthesis. You probably learned that it was 6 carbon dioxide plus 6 water gives me a glucose and gives me 6 oxygen. However, you are going to learn that that was not right.
When your life is a lie.
That is a simplified equation, so technically it's correct. But if you want to know what's really going on and want to truly understand the processes, you have to include 12 waters going in and 6 waters coming out. Because over the next few days, you will learn that it takes 12 waters to get going, and then a separate process is making 6 waters. Now, true, these 6 waters probably photosynthesis. The first phase is known as the light-dependent phase, and this occurs in and around the thylakoid membrane. So this occurs in and around each thylakoid. It's the light-dependent phase. Then after this comes the light-independent phase, and this happens out in the stroma with the help of several enzymes. So the light-dependent phase is dependent on light, and the light-independent phase is dependent on the products produced during the light-dependent phase. However, if you turn out the light, they both stop. Okay? Because the products used in the light independent phase will run out quite rapidly. So it'll be like comes to a stop. Today we're just going to talk about the light dependent phase. Tomorrow we'll talk more about the light independent phase, also known as the Calvin cycle. Okay, we're going to go over this a couple times. You probably feel like you're confused, and that's fine. I expect it. All right, what's the first thing we need to do photosynthesis? Light, yay! And then the second thing we need? Water. All right, so the first thing we have to do is we have to take sunlight energy, and we're going to use that energy to help split water, right? So essentially what happens is we've got chlorophyll, and we've got some enzymes, and we're going to take sunlight energy, and we're going to take water in, and we're going to break apart the water. Now the water molecule gets broken apart so violently that not only do I get an oxygen all by himself and hydrogen, but I also rip the electron off of my hydrogen. So now I've got a proton. I got two protons because it's water, H2, right? I got two protons hanging out with no electrons, and I've got a water waiting for, I got an oxygen waiting for another oxygen. And then when that second oxygen comes along, they're going to partner up the O2, which is a gas, and they're going to diffuse out of the chloroplast. Now, in the porphyrin ring, I've got that magnesium. And so what happens is, when the light hits it, it's going to knock off an electron. It's going to fly out and go do some work. Okay? But now I've got a magnesium in there that's like, hey, I lost my electron. Right? So it's going to get replaced by this breaking up of the water here. Okay? So I'm going to replace that electron. So it's going to just keep losing it, getting a new one, losing it, getting a new one, losing it, getting a new one, over and over and over again. Okay? There's an enzyme that's going to be breaking up the water, and we'll talk about more of the enzyme. Now, once I've done all that, I've got protons that are going to do some work. These protons are going to do some work, and we're going to make some ATP, and we're going to make a new molecule that you haven't heard of yet called NADPH from these. So NADPH and ATP are going to be used later in the Calvin cycle, along with our carbon dioxide, right? And they're going to come together in the Calvin cycle. We're going to make some water, so 6 waters, and we're going to make a molecule called triose phosphate. So this is in the chloroplast. We are making triose phosphate. That is the end product of the Calvin cycle and of photosynthesis. Now, this triose phosphate is a 3-carbon sugar, right? Triose, ose is sugar, right? It's going to, excess triose phosphate is going to leave the chloroplast, go into the cell of the plant, where the plant has enzymes that are able to change this triose phosphate into different things. One of the things is it's going to take 2 triose phosphates, there's an enzyme that will slam them together, knock off the phosphate, and we have glucose. glucose. Yes. Right? How many carbons are in glucose? Oh my God, you guys are terrible. 6. So if I have a 3-carbon sugar triose phosphate, I only need one more. Okay. All right, let's talk about this. All right, let's look at the photosystem.
Photosystem 1 and 2.
All right, so photosystems in green plants are protein complexes that are used to harvest light energy so that it can be converted into chemical energy. That is, the chemical energy is ATP and NADPH, known as nicotinamide adenine dinucleotide phosphate, which I will never test you on. I will only ask you about NADP plus and NADPH.
Will you test the honor students on that long annoying name?
No, no. Even in college, we only had to do NADP plus and NADPH. Nobody says that long. Right. So this happens in and around the thylakoids of the chloroplast. Now, the photosystems are in the membrane of the thylakoid in the chloroplast. Now, here's something that you should know, because this is confusing. And this is what the scientific community decided to do, because heck, let's confuse students. Alright, the first photosystem that you start with is photosystem 2.
What?
Alright?
Yeah.
And then later we will deal with photosystem 1. And the reason is we discovered photosystem 1 first. And
Oh
then
my
photosystem
God.
2 later. And then they had a convention. And my hypothesis is the guy who discovered this said, "No, I found it first. It's staying number 1." And they just let him do that. So it stayed that way ever since.
What science rules committee creates this type of garbage? The name is.
Oh, there's going to be stuff like this all year that just makes absolutely no sense. My favorite is in genetics, where there's 2 different things that have the exact same name. Alright. So, we're going to start out with our light. Coming in to photosystem 2. Alright? We're going to have an enzyme that's right in here, that's kind of hanging out right next to photosystem 2. And it's going to use some of the charged energy that occurs there. Alright? And it's going to take water molecules and break them apart. Okay? Now, that light energy is also hitting our porphyrin ring, vibrating it violently, and knocking an electron off the magnesium that's in the center. And there's lots of chlorophyll A inside inside of both photosystems, right? So it's going to knock that electron off, and now we've got a magnesium that's like, hey, I need an electron, and then it gets replaced by the water that's being broken. Right? So it's like, yay, I got an electron. Then bing, proton hits it and it loses again. So these guys are just transferring electrons, essentially, as long as there's light. Okay? So, I've got my water that's broken. 2 oxygens are going to meet up from 2 different water molecules broken, and they're going to diffuse out. Right? They're going to leave. Okay? So it's a waste product. The oxygen gas that we breathe and that we don't depend on, our mitochondria do, which we'll talk about. Right? That oxygen is going to diffuse out and be used by the mitochondria. Now, meanwhile, we've got these hydrogens, right, that are now protons, right? They don't have an electron, and they start building up in here as we're breaking water. And then the electron. Okay, we kicked off an electron, and it's going to go down what's called an electron transport chain. Okay? And as it moves through these enzymes in the thylakoid membrane, one of them is a proton pump. This proton pump is going to use the energy by the momentum of the electron to pull any protons that are out of the stroma back into the thylakoid membrane, so the thylakoid space, inside of the thylakoid. Okay? So not only are we getting protons building up in number because we're breaking water, but we're also pulling them in from the outside. So we create a concentration gradient of protons inside of the thylakoid. That means there are more inside than outside. And what do they want to do?
Go
They
outside.
want to get out because everything wants to be at equilibrium, right? So they want to get out. And it just so happens that my most favorite enzyme, ATP synthase, is their only escape. Alright. Now ATP synthase is my favorite just because it's so cool, and without it, we're dead. Right?
Isn't that amazing?
Yeah. So ATP synthase is cool because it has a hollowed out center core, essentially. And it's the only way that the proton can get through. And what's neat about that core is that it's like a spiral. Right? So the pressure of the proton going through it, as it spirals through to get out, causes the ATP synthase to turn. Right? And as it turns, it's going to grab an ADP molecule, and it's going to grab a phosphate group, and it's going to slam them together and spit out an ATP.
Ooh. Smart.
As it turns, grabs ADP, phosphate group, pushes them together, and spits it out. Right? So you get about 1 ATP for every turn.